Okay, guys, today we're going to go through section 3.4, which is called the Bronstead-Lowry acid-base concept. So we're going to introduce a new idea of how we define what an acid and what a base is. So in grade 11, we learn what's called the Arrhenius theory. So the Arrhenius theory uses the following data. Acids are substances that will react with water to produce hydrogen ions plus an anion. So really the hydrogen ion is that hydronium ion. So if I'm just imagining what an acid reaction looks like, I know hydrochloric acid is an acid. When it reacts with water, we're producing hydronium and the anion, so the anion chloride. Bases will dissociate in water to produce a hydroxide ion plus a cation. So a strong base that I know would be sodium hydroxide. When it reacts in water, we actually don't show like a reaction overall. We just show that we understand that strong bases dissociate into their ions in water. So therefore, we define sodium hydroxide as a base because it produces hydroxide. We define HCl as an acid because it produced hydronium or hydrogen ions. But the Arrhenius theory has lots of limitations. So the limitations were that it doesn't predict acidic and basic properties of some compounds. So sodium carbonate is a base. But if I dissociate that in water, I'm not producing a hydroxide. So a base can't be definite, like 100% defined as just something that produces a hydroxide. Aluminum chloride, that's acidic. It has acidic properties, but it doesn't have a hydrogen, and it's not going to form hydronium when reacted in water. So how are we to explain the properties that compounds like this have? So the Arrhenius theory is more of a basic idea, so that's what we do it in grade 11. In grade 12, this is also just explaining the Arrhenius theory again. In grade 12, we're going to learn the Bronstead-Lowry concept, which will change the definition of an acid and a base from the Arrhenius theory. So Arrhenius, once again, they produce hydronium, they produce hydroxide, and the same limitations. So another limitation to note at the bottom of the page here, substances can do both. So it can have an acidic and a basic property depending on what it's reacting with. So that means it's called amphiprotic, basically, is meaning it could do either. So the Bronstead-Lowry concept is the new idea we're going to look at today. So it's by obviously two scientists, last name Bronstead and Lowry. So it has a new definition of what it means to be an acid or a base. We're going to discuss the entities again. So back when we did redox, we would list every entity in our reaction. So we're going to do that also here. In redox, an entity was something that was either being like an oxidizing agent or a reducing agent. Here they're going to be acting as an acid or acting as a base in the context of our question. So the definition of a Bronstead-Lowry acid is anything that acts as a proton donor in a reaction. And a proton basically being hydrogen. So a hydrogen donor, hydrogen is the same as like the hydrogen atom itself just contains one proton. So one proton and one hydrogen atom are the same thing. A Bronstead-Lowry base is a proton acceptor. So whatever in our reaction is accepting the proton is considered a base. Whatever in our reaction is donating that proton is considered to be an acid. So this is just the key idea you want to take away from the Bronstead-Lowry concept. Proton donors are considered acids. Proton acceptors are considered bases. So let's show a few examples. A Bronstead-Lowry reaction involves a single proton transfer from one entity, which would be the acid, to another, which would be the base. The acid is always donating that proton to the base. So if we're writing out hydrogen chloride in water, which is the same reaction I really just wrote earlier. So hydrogen chloride in water. Hydrogen chloride is my acid. It's going to act as a proton donor. So it will give away that proton to the water, meaning now we have the anion left behind, and that hydronium ion also present in the solution. Now, that's the exact same reaction we kind of showed before with the Arrhenius theory idea, but Bronstead-Lowry's idea, it's doing the same thing. It's just going to incorporate a lot more reactions other than just these basic ones in the system. Ammonia is a good example of why Bronstead-Lowry's idea works. If I react ammonia in water, we know from using ammonia that it typically has basic properties. So if it's a base, it would have to be a proton acceptor. So this time, water will act as the acid and donate one of its protons to that ammonia. And that would leave us behind with the ammonium ion and a hydroxide. So that shows that we're producing hydroxide, so similar to that Arrhenius idea. But this kind of shows the chemistry of why it works, why we know for sure that it acts as a base, and this is the chemistry behind how that base reaction is proceeding forward. I don't know if there's another one on this page. Oh, hydrochloric acid and ammonia solution. I think we'll kind of get to a more complex example like this later. I don't want to do this just yet. Okay, water has the ability to either accept or donate a proton, making it amphiprotic. So amphiprotic meaning exactly what it says. It could either donate a proton, act as an acid, it could accept a proton and act as a base. Regardless, it just depends what it's reacting with. So if it's reacting with a stronger acid, it will become the base. If it's reacting with a stronger base, it will become the acid. And here are some examples of other amphiprotic substances. So basically, like any hydrogenated or any hydrogen polyatomic ions are examples of things that could be amphiprotic, because technically, like HPO4 2-, it has a negative charge, so it's definitely willing to accept a proton. When it accepts a proton, I could write it as H2PO4 1-. It also has a hydrogen available to donate. So if it donated that proton, then it would be back to just its like polyatomic ion state. So that means it can act as an acid or a base depending on the scenario. So similar to how when we did redox reactions, there was certain things that, like copper, for example, could act as an Ra or an Oa depending on the scenario. Same thing here. So these are all options that you could see as something that could act as a base or an acid. And when you're labeling any of these, you want to label base or acid, and then we're going to discuss the relative strengths. So they're talking about hydrogen carbonate here. So it's amphiprotic because, and then I guess we could just show down here. So I'll show that it could accept a proton. So if I have HCO3- and I react it with water, water could donate a proton to it. Giving me H2CO3. I guess it wouldn't be minus anymore, it would be neutral now. And I would have hydroxide in solution. So this would be it acting as a base, so it's accepting a proton. It can also be a proton donor, so it could also donate the proton. So this time I'll show the hydrogen tracking up here, and it's donating that proton to water to form hydronium and leaving behind just the ion, CO3 2-. So this would be it acting as an acid, acting as a proton donor. So this is why like baking soda is something we use a lot. It has the ability almost to like form that buffer. It can either act as an acid or a base in any substance to act in either way, I suppose. So amphoteric is kind of the word to describe the overall substance. Okay, on the next page, we're going to start discussing conjugate acids and conjugate bases. So when we do a Bronstead-Lowry reaction, equilibrium arrows are going to be important. If they don't tell you that it's at equilibrium, then you would assume it's like a qualitative reaction that goes to completion, so has more than a 99% yield. In most reactions, we will be using those equilibrium arrows, but you should be able to tell when you read a question what arrows you need. So Bronstead-Lowry, usually the acid and base reactions are at dynamic equilibrium, which we know means that the rate of the forward and reverse reactions are occurring at the same rate and at the same time. And they're showing us kind of like a little description below of what is happening here. So we're seeing that we have an acid that is donating a proton to water. So that means water is acting as a base in this scenario. After, in the products, I suppose, we have an ion right here. It has a negative charge, and then H3O plus. Now, if I look at the reverse reaction, this side is now my reactants. So if I'm comparing these reactants together, H3O plus is going to be my acid, the anion will be my base, and that's going to donate the proton back over, forming said products. So a pair of substances that differ by only a proton is called a conjugate acid-base pair. So this acid is a conjugate, has a conjugate base, which is this. The only difference between them is they differ by one proton or one hydrogen. Same here. Water is a base in this case. Its conjugate acid would be hydronium. It has one extra proton. Okay. And that term conjugate means connected, so that means they have a relationship to each other, just one hydrogen in the difference. Whether that hydrogen has been added or taken away depends on whether it was an acid or a base originally. So, look at a few examples here. So we're talking about acetic acid. It says it has a strong attraction for its own proton. So if I look at what acetic acid is, CH3COOH, down below, here's my formula for it. We know acetic acid like regularly as vinegar, and we use vinegar in cooking for like a less harsh cleaning product. So I think you would be able to like understand from a realistic standpoint that vinegar is a weak acid. If it was a strong acid like hydrochloric acid or nitric acid or something, it would burn through more substances and we wouldn't be able to keep it in our kitchens. So acetic acid is a weak acid because it doesn't readily donate a proton. So reminder, the definition of an acid is something that donates a proton. So if this weak acid, it will donate its proton, but it really doesn't want to. It has a strong affinity for it. It wants to. Affinity means it has a strong likeness, like it wants to hold on strongly to its own proton. And its conjugate base, the acetate ion, so this guy right here, is a stronger base than water. It has a greater attraction for protons. So that means at equilibrium, right here, since acetic acid is a weak acid and it really doesn't want to donate its proton to water, it would rather hold on to it. The forward reaction has a really low percent yield, that 1.3% right there. CH3COO minus, that acetate ion right here, is a strong base. Hydronium is a strong acid. Therefore, the reverse reaction would be at a much higher yield in this case. So just kind of an interesting thought process, just when we compare. And I'll teach you the process of how to like come up with this yourself as we go. But it's just the difference between strong and weak acids. So then if we compare this to HCl, hydrogen chloride molecule has a much weaker attraction for its own proton than water. So HCl, it doesn't have a strong connection to its hydrogen. It would readily give it up, meaning that it's a great proton donor, so it's a very strong acid. This is a good statement here. The stronger an acid, the less it attracts its own proton, and the stronger a base, the more it attracts another proton. So HCl is not attracted to its own proton. It is readily going to give it up to water. And you can see that this doesn't even have an equilibrium arrow. That shows that like the forward reaction is the greater than 99% yield reaction. Okay. Also might just add a couple points here. I think that it's down below. Yeah, sorry, I'm going back to the acetic acid slide. So if an acid is weaker, acid and base strengths are inversely proportional, meaning like if an acid is weak, its conjugate base would be very strong. So that's shown right here. I know vinegar is a weak acid. Its conjugate base, the acetate ion, is super strong, and that's pushing the reaction with a higher yield in the reverse arrow. Same thing here. If I put reversible arrows here, this would have a very, 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 very low percent yield. A stronger acid has a weaker conjugate base. So the conjugate base to HCl is just chloride ion. So that's going to be a very weak base, and the reverse reaction obviously here isn't even necessarily occurring at any significant amount. It's not shown. So acid and base strengths are inverse. A stronger acid is a weaker base, and a weaker acid has a stronger base, conjugate base. Very similar to the chart for RAs and OAs. So the strong RAs, if something is an RA, it would be a very weak OA when they're at the same level. I think in your notes there's a nice summary of everything that kind of just happened there. It's a good read through. And now we're heading just to the paragraph below where it says predicting acid-base equilibria. So this is where we're actually heading to like solve some problems here. So according to both theories, the substance has the greatest attraction for protons, which would be the strongest base. So whatever wants the protons the most will react with the substance that will give up the protons the easiest. So basically, always think about the fact that the base is looking to accept protons. The strongest acid wants to give protons away. And we're typically assuming only one proton is transferred for collision. We may look at a few examples with more as we go through. So in a system that has lots of different possible acid-base reactions happening, we know that like now that we're seeing things at equilibrium, there's lots of forward and reverse reactions happening. So when I add entities into a reaction, the only significant reaction, the one that we will focus on, is the proton transfer from the strongest acid and the strongest base. So we have to decide everything that's being put into a solution. What is the entity that's the strongest acid? What is the entity that's the strongest base? Okay, and those two things we will write reacting with each other. Okay. So when we add things into solution, we represent the entities as they exist in solution. So I would look at what I'm given in the question. I'm going to read what I'm given, and then I'm going to use this chart right here to decide how to list those entities. So if they tell me that I have sodium chloride in solution, so I have an ionic salt, and that's not just sodium chloride, it's any ionic salt, like a metal and a non-metal. We write them as their ions. Okay, so that's how they would exist in water, is broken apart into their ions. If I'm given a strong acid, and all the strong acids, please go to page 8 and 9 in your data book. So on page 8 and 9, there's a chart of the relative strengths of acids and bases. Now, you'll see that we've talked about this chart before. The top 6 acids listed, 1, 2, 3, 4, 5, 6, before the hydronium ion, are all the 6 strong acids. So if it's any of those 6, we list these entities. Those are the entities that we have present. Okay, so we know that it would react with water. I'm going to list H3O plus and the anion. Okay, so those are the entities that we will list in solution. We are not listing the acid written as itself. We're listing the product entities in solution. If it's a strong base, any like metal hydroxide essentially, like group 1 or group 2 metal, we list them as their ions dissociated in water. Okay. And we're always going to list water itself as an entity, which is why you don't have to worry about listing it like this. So we're not listing NaOH, we are listing sodium and hydroxide separate in their ionic form. If we have weak ones, like a weak acid or a weak base, then you list them exactly as is. So you do not write them in like dissociated or ion form. Okay. So here's our steps. So if we're being asked to predict the predominant acid-base reaction, so we're given us certain things are added into a reaction, and we have to say what would be the predominant reaction, the overall reaction, okay? Then our steps are as follows. List all the entities as they appear in solution, including water. So same as in like the OAs and RAs with acids and bases, we always included water as a part of the reaction because we're typically dissolving things in water. All solutions have water. Number 2, label all possible aqueous acids and bases. So we go through each entity, we label it as an acid or a base. And then number 3 is the most important step, I feel. Label the strongest SA and the strongest SB. So the strongest acid and the strongest base. And you're going to use your chart on table, that was page 8 and 9, that relative strengths chart in your data book to make this decision. So on the chart, the top 6 acids are listed up there. Our acid formula is shown beside them. Now the acid strength gets lower as we go down the page, and the base strength, the strongest base, starts at the bottom of the page, hydroxide OH minus, and you go up the page for bases. So down the page, strongest acids are at the top. I guess I'll just write it like this. Strongest acids, weakest acids, weakest bases, strongest bases. So similar to that OA and RA type of a pattern, on the chart, all of our strong acids are in the top right-hand corner, our strong bases are in the bottom, or sorry, in the top left-hand corner, and our strong bases are in the bottom right-hand corner. Okay. So once I have the strongest acid and the strongest base, we are going to write an equation using the strongest acid and the strongest base and show that proton transfer. So we're going to write an equation that shows the transfer of 1 proton from the strongest acid to the strongest base. And then the products will be the conjugate base and the conjugate acid of both reactants. And then the last step is important. We're going to predict the position of the equilibrium. And the way that we do that is we always base it off the fact that the side opposite of the strongest acid is always favored. So if the strongest acid is on the left-hand side of our equation, our products will end up being favored, which means we have a percent yield higher than 50%. So percent yield greater than 50%. If our strongest acid ended up being a product, one of the conjugates, then our reactants are favored and we have a percent yield of less than 50% moving forward in this reaction. So we're going to follow all these steps and do 2 examples right now. So for the first example, what is the predominant reaction? So when we mix all this stuff together, what is the overall reaction we're going to care about? So it says, what if spilled drain cleaner sodium hydroxide solution? So I'm just going to write down what I was given. I have a sodium hydroxide solution is neutralized with vinegar, and vinegar is acetic acid. Okay. So based on the fact that I'm listing out my entities now, so maybe I'll list them over here. Oops. Sodium hydroxide, I know that's a strong base, so I list strong bases in their dissociated form. So my options are sodium ion, hydroxide ion. Acetic acid is a weak acid. If you look on your chart, it's down on the second page on page 9, the second from the top, CH3COOH. And it's a weak acid, so I write it as is. And I always have water, also as an entity. So now I'm going to go through and label each one as an acid or a base. Now, a sodium ion is neither an acid or a base. It's not listed on that conjugate acid, conjugate base formula sheet. OH minus, hydroxide, that's a base. It's listed in the base column. Water could be an acid or a base. It's listed in 2 locations. At the very bottom of the page, it's an acid. At the top of the page, it's the conjugate base to hydronium. So it could be either. And CH3COOH is a weak acid. so it's also an acid. So same as before, I list all my entities. I give an explanation of whether each one is an acid or a base, and now I'll go through and choose what's the strongest acid, strongest base. So my strong acids, I'm comparing acetic acid and water. Now water is at the bottom of the list for my acid strength. Acetic acid is above it. So acetic acid is our strongest acid. I'm also comparing water with now hydroxide for the strongest base. Now hydroxide ion is at the very bottom of the right-hand side of my chart. That's where the strongest base lies. Hydroxide is the strongest base possible. So strongest base. Water is way up at the top of the base chart. So that means it's very weak base. So now we're going to follow step 3. Nope, 4, sorry. We did step 3. We labeled the strongest ones. Step 4, we're going to write the equation showing the proton transfer between the strongest acid and the strongest base. So the strongest acid in our solution was acetic acid. The strongest base was hydroxide. And when we follow Bronstead-Lowry's ideas, we transfer a hydrogen from the strongest acid to the strongest base. So our products, I'm just going to erase these right here. So we would be producing the acetate ion and water. So all of these are aqueous here. I just didn't put my states in. Okay, it looks balanced to me. Everything's good there. Now I am looking at identify the acids and the conjugate bases and acids. So here, this was my acid. This was my base. The acetate ion is the conjugate base when we use acetic acid as an acid. And water is the conjugate acid for hydroxide. And we are listing proton donors and acceptors. Did that too. Proton donor showed it with that the acetic acid is it. On the other side, if my reaction is moving forward, water would be my proton donor. Just showing water would give a proton back to the acetate ion, and then the reaction is reversible. Okay. And then just looking at, is this favoring products or reactants? So out of the 2 acids listed, my 2 possible acids in the forward and reverse reactions, so forward and reverse reaction, are acetic acid and water. So water is an acid right here. Acetic acid is a water on this side, is an acid on this side. Oh my goodness. Acetic acid is an acid on this side. Water is an acid on this side. So comparing those two, we know acetic acid is the stronger acid over water. So we are favoring the product side, the opposite side of the strongest acid. Therefore, this would have a greater than 50% yield. So that's the answer we're looking for, showing all of those things. Okay, one more. There's not really any room here. I guess I'll extend the page. Okay, this one says ammonium nitrate fertilizer is produced by the quantitative reaction of aqueous ammonia with nitric acid. Quantitative means no equilibrium arrows. It's gone fully like a 99% yield. So write a balanced acid-base equilibrium equation. Identify the acid, base, and the conjugate acid, conjugate base. List the proton donor and acceptor. Okay. Our entities is that we have aqueous ammonia. Ammonia is NH3. Ammonia, is that on my chart here? I'm just trying to look. It might not be listed. Okay, yeah. Ammonia is listed down at the bottom. It's listed as a decently strong base. I'm not going to show that, like, it's not a hydroxide one. Like, it's not like sodium hydroxide, lithium hydroxide, or something like that. So I don't need to show its dissociation. I can leave it just as NH3. nitric acid is one of the top 6 strong acids. So that means when I list my entities, I'm going to list hydronium and I'm going to list the nitrite ion. Going down my chart, and I also guess I have water as an entity always. So let's label what everything is. NH3 is usually a base. NO3 is a base. I can see it in the conjugate base column right there. That's how I'm making that decision. H3O plus is an acid. And water could be an acid or a base. And now the last piece of information, let's identify what's the strongest acid. So we're deciding between hydronium versus water. Obviously, hydronium is higher on that list. So that's going to be my strong SA. So my reaction will start with hydronium, adding to my strongest base. My options are water, NO3, and NH3. I'm looking for the one of those that exists closest to the bottom right-hand corner. So that would be NH3 is my strongest base. And I'll show this qualitative reaction. Since water or hydronium is acting as the acid here, it will donate a proton, leaving me behind with water and NH4 plus. Listing what everything is. This is my acid, my base, my conjugate base, and my conjugate acid. And just showing, I did show my hydrogen moving across the system. Okay, you can try the practice problems from 3.4 now. I think next week we might get through 3.5, and that might be it for this chapter. And then we'll do a final summative assessment on these last 3 lessons, and we're basically running out of time to be finishing up. We're almost done, Chem 30. So please call in if you have any questions on this stuff or need any help. If we don't hit one of the lessons, it might be the last one, 3.6, which is on pH curves. You did learn some of the basics on pH curves in Chem 30, or Chem 20, sorry. But if you are interested, I could probably put up a video just for like interest's sake in case you wanted to just go over the lesson yourself. Okay, thanks guys. Try the 3.4 questions and we will go from there.